Yeah, so the first approach that we learned about how to speed up ray tracing was based on so-called object partitioning. So what we did is we grouped objects into disjoint groups. We divided the objects into disjoint groups. So for example, if we do hierarchical bounding boxes or bounding volumes, we can group these three objects here and we can group these two objects here. And then we just have to do two initial intersection tests. In this case, it doesn't save us anything because we have both boxes intersect with the ray, so we have to check the objects in both objects. But if you have more, then you can imagine that this can save you a lot of intersection tests. But what we do here is we group the objects into distinct groups, so each object is contained in just one particular group. But of course, those groups can overlap. Like you see here, you have an overlap of these two boxes here. And the second approach that we have is so-called space partitioning approaches, which are kind of the opposite of it in a way that we partition the space. We do not do the partitioning based on the objects, but we do it based on the space. So for example, we can define a grid structure. So that should be equally sized cells here, because we're not considering the objects, we're considering the space. And then we can check which of those cells intersect with the ray, and these are of course these here. So we don't have to check for intersections in these cells because they don't intersect with the ray anyhow, but we only have to check these ones here and then do an intersection check with the objects that are in these cells. And you see here that it is opposite insofar as in the other case each object was within one box or one field that we defined, whereas here, but the fields didn't cover the whole space and they could even overlap, whereas here the fields uniquely separate the space, but of course then the objects are not nicely organized within those cells, but they can, like we have it in all those cases here, be part of several cells, which makes then the individual object check a little more difficult. And of course the most straightforward, or probably the most simplest approach to do this is just use a regular grid and then traverse our array and then see if those cells, what cells intersect, and if they intersect, then we do an intersection check with the objects that are in this particular cell. And the traversal is pretty simple because we can see this as a starting point, ij, in a matrix, and then when we walk along this, we just have to either increase, or, well, if it's in that direction, if this is positive, if this is 0, 0, then we have to decrease the j value, or we have to decrease j minus 1 or I minus 1. So we just have to, we have this cell ij, and then if we have a line, it's clear that we either go to this neighboring cell, or if the ray moves down, we go to the cell below. Or in this one particular case where it goes directly through the intersection points, then of course we have to increase I and j at the same time because we have this situation here. But you see that we can just go to one cell, check it, and then look where the ray exits, and then we know where the next cell is. So the traversal here is quite simple and straightforward. What we have to be a little careful about is the intersection check with the actual object, because like I said, the objects are not necessarily contained within one cell. So for example, if we have an object like this, or two objects, one is here, the other one is here, and we have a ray that shoots here, then if we check the ray intersects with this cell, it's too hot today, even for the software. So we see here the ray intersects with this cell, so we see this object is in the cell. So if we do the intersection check, we see, oh, it intersects. So this is our intersection point, and we don't, if we're just interested in the first object hit by the ray, we don't even continue here, and we get a wrong result because this is not the point we see on hit by the ray, but this is the point that is hit by the ray. So we have to be careful that we do the intersection check either with the part of the object that is in the cell here, or we do it with the whole object, but then we have to check if this intersection point is actually within that box or not. So it is a little more complicated, but not too complicated. It's just something we have to be careful and take care of. And you see that this is a pretty simple and straightforward approach and can again save you a lot of intersection tests by just using a uniform spatial subdivision by having this regular grid. But of course you can think about different examples. So for example, what do we, if we have like a lot of objects here and a lot of objects here, then you could say, why would I need a grid that makes a very detailed separation in these cases here? Wouldn't it be better to just have, like similar to the bounding boxes, a grid that goes, for example, like this, where we just have 4 boxes and we check them? That would save us a lot of individual intersection tests that we would have to do with this uniform grid. And this is exactly the idea now of this non-linear, non-uniform spatial subdivision. And one of the most common approaches, and this is actually also the most common approach, something that is very much used in games when you do the ray tracing in games for the intersection tests. It's the so-called Octrees approach. So if there is one thing from the ray tracing lectures that is important for games, it's probably this one. The Octrees is like a 3D version of a quad tree, and the reason why I'm saying this is because I explain it only into 2D because it's much easier to draw. But if you understand the basic idea of quad trees and how the separation is done with quad trees, you should be able to easily generalize to 3D, because it's just a straightforward generalization to a third dimension from squares to cubes. So we have intersection with squares in 2Ds or rectangles in 2Ds, and then cubes or 3D rectangles in 3D. Good. So the way how this works is we take space, and in this case the objects are just illustrated by dots. Usually we have triangles, but this is just a straight an illustration to illustrate the basic concept, so I'm sure you can generalize with that. What we do is we start with a large bounding box that contains all the objects. So if we have a scene where there are only a couple of objects in one area and everything else is free, then we already, of course, save some intersection tests. For example, all arrays that don't hit this bounding box, we don't have to do individual checks. But of course, this is a very huge bounding box because it contains all our objects, so we want to split that. So we just do a uniform, the smallest possible uniform subdivision, which is splitting a box into our bounding box into 4 equally sized sub-bounding boxes. So in this case, they're coincidentally squares, but if we have, if they're not square, then we have rectangular boxes. But the next step would just be from 1 rectangle to 4 rectangles by splitting them horizontally and vertically equally. And then we say, okay, we want to have cells now that contain a maximum amount of objects. So for example, let's say we want to go till a number 2, maximum 2 objects per cell. So we see here there are more objects in these cells than we have. So here we have 6, here we have 5, here we have 6, and here we have, here we have 1. So we say, okay, this is a cell where there is just 1 object. If we split that cell further, then we do a lot of unnecessary intersection tests. So for example, if we do this even further, we have to do here 1, 2, 3, 4, 5, if a ray goes here through. But there is just this 1 object, so we just leave it that way. So we don't do this separation here, but we only split the parts where we have more than 2 objects. So we split those here, and then we see here, these are all 2 or less. So we don't do any further splits here, but here we have 5, and here we have 3 and 3, so our conditions is not fulfilled here. So we do another split here, and now we see that all the boxes have smaller or equal to 2 objects. So now we stop here, and you see that this is a grid that is not uniform, but it resembles much more the situation that we have with the distribution of the objects. So this saves us a lot of intersection tests, but of course this comes at a price, because the intersection test, the transversing those with the ray, those cells with the ray, is not as straightforward, because here, for example, we cannot. Here we also just increase the index. We know we go to the left, to the right, or we go up, or if it goes directly through this intersection here, we go in this diagonally attached cell. But here we also have to decide, do we go in the upper or in the lower cell? So it becomes a little more complex, but with the benefit of not having to do, for example, here 3 intersection tests if we would have split this as well. Good. So this resembles the distribution of the objects a little better, but you can still argue, well, we still have squares or rectangles here. What happens if we have something like this and, for example, something like this? Wouldn't it make more sense to have a cell here and a cell here, or maybe an ellipse here and an ellipse there? Of course this would make more sense, but the problem is then, of course, the construction and the intersection tests become more complex. But a good compromise of this would be to have something that is less squarish but more like in a rectangular shape, and this can be achieved by so-called binary space partitioning, with binary space partitioning trees, or BSP trees for short. So let's look at how that works. For BSP trees, we basically say we split the space by one line in 2 halves in each step. So we start with the first step where we say we count the objects, and then we split them in an equal size. So for example, in this case we have 9 objects here and 9 objects here, so we split them in the middle. More or less equal size, of course, because we can have the situation that we have an uneven number of objects, then there is one space has one object more, or we can have a situation that we have like 4 objects, and because the calculation is much easier for the transversion and the intersection if we have lines that are parallel to the coordinate axis, which is why we only split horizontally and vertically. But if then you have 2 objects that are in one horizontal vertical line, for example, then of course you have to split them in a way that you get an uneven distribution of the objects, but it is more or less equal size. And then we have 9 objects, so we want to narrow it down to have cells with less objects. For example, again, we say we want to have maximum 2, so we split again. But since we have split it horizontally now, vertically now, we say we split it now vertically, so we get a better match of the distribution. So here we see we have here 5 and here we have 4. So this is an example where we don't have the same number. Again, here we have 4 and 5. And then we say these are all still less objects now, but still more than we want. So we split it again. Now we see here we have 2, here we have 1, here we have 2, here we have 2, 2. But here we have 3, 3, and 3, so we have to do another split. And now we see all our objects, our cells have less or equal to 2 objects, so we're done now. And we have now a distribution of the space that is not uniform, and that should match the actual distribution of the objects a little better than this squares that we took. Actually, if I look at this example, I don't really think it's that convincing, because I kind of intuitively would say the example with the squares we had looked a little nicer. So I'm actually not sure we would have to do like a real draw array and check how many cells we really save here with this compared to the other one. but I didn't bother about finding a good example for it. But I think because I think this is a very good exercise, and I think it's actually an exercise of the tutorials, that you're supposed to think about yourself. What would be how would a distribution look like where this kind of splitting of the space be a good approach and save you a lot of time, and what would be a distribution where this approach would actually result in a very bad partitioning of the space. So because I think this helps you a lot in understanding the characteristics of it, which is why I will not do it here, but you're supposed to do it as an exercise. Now, of course, for the traversal, we have to think about how we can do that, and here I like to draw your attention to what is written here. I was always talking about binary space partition trees, but I never really drew a tree. But the point is, you can easily create a tree with this partition. So let's do that. We start it with the first split. Let's call it the split line A, and that becomes the root of our tree. So the node of our tree always represent the splitting lines, and the leaves of our tree then later contain the objects that are part of this last to the left or to the right or to the top or to the bottom of the last splitting line. So we start with the root because we split first on this line A. Then we see the left and the right side still have more objects than we want, so we split this again. Let's call it splitting line B1 and B2, and you see now we do a horizontal split because before that we did a vertical split. So A is again split into two subspaces, or A splits our space into subspaces, which in turn are again split into other subspaces. So we get here B1, B2, and then again we split it because let's call it C1, C2, C3, C4, C1, C2, C3, C4. So you see here each node has two children because after each node represents a splitting plane, and there are always a splitting plane always splits the space in two halves, which is why it's called a binary space partitioning tree. So that's where the binary comes from. So we always have two sons. Each node has two children, and then for the C we see here we don't split the left part, but we split the right part. So on the left side we get the actual objects, but on the right side we get another splitting line. Let's call it D1, and that one is D2 then, and that one is D3. So we get here the splitting line D1. For C2 we see we get a splitting line D2. For C3 we get nothing, and for C4 we get a splitting line to the left, D4. And you see here the way I was drawing it, I did this on purpose because we usually say that the left subtree gets the upper or left cell if it is a horizontal or a vertical split. So you see here, if I'm splitting it to the right, then I make this the right subtree, and that of course then makes it easier for the traversal. And then we put the actual objects in, so let's just call them 1, 2, 3, 4, 5, and you see here that this is 1, 2, this is object 3 to the left, and to the right we get object 4, 5. And then the same here, of course. So you see here for these nodes here, the C1, C2, and C4, we have the one side is split by another splitting plane, so we get another node, whereas the other side, there is no further splitting, so we get a leaf which contains then the actual objects. And then when we do the intersection, we basically do a first check here, and then we can decide if both sides intersect, or if one side doesn't intersect, we know that we don't have to look into the left part. So for example, if we have an array that starts here and goes up here, we know immediately after checking A that it will not intersect with all the cells that are in this part of this tree, so we save a lot of intersection tests here by just throwing that part away from the tree away. So this is quite similar to what we had with the hierarchical organization of bounding boxes. Good. Yeah, so these are the BSP trees, but as I said, in game programming, usually Octrees are used. Are there any questions related to this or to ray tracing in general? No? Yeah. If the objects are... Oh yeah, you mean a situation like this. Then, of course, the splitting becomes more difficult. Yeah, in a situation like this, you would probably hope that there are more here. And then I would say that would work well if you have more here. And but of course, if you do it with this here, no matter how you do it, you have to cut an object. So in this case, the binary space partition wouldn't bring you any benefit. But that is exactly the problem with all these kind of optimization approaches. They usually depend on certain situations, and if a certain situation has certain characteristics, they work very well. But then there are always examples for situations where they work horribly well. That's, I think, a general problem with heuristics, that they usually work well on average or work well in certain situations, but not in other situations. Good. So, yeah. If there are none further questions, then we're basically done with the ray tracing and almost done with the lecture. So just as a short memory, also to finish up the ray tracing part, in the lecture we talked a lot about projective methods and very few about ray tracing, because of course ray tracing is an important part of graphics, but for game programming, for the reasons I hope you understand now, interactivity, speed, hardware support, projective methods are very often used, and we already saw that you can also produce very realistic results with projective methods, but also ray tracing is becoming faster in their approaches for real-time ray tracing, so it's kind of approaching each other in terms of speed, but also in terms of quality. So to wrap up the things, if we look back, you see that we covered now all chapters from chapter 1 to 13 of the book, which is quite a lot for such a short course, I would say. So if you learned everything that I was telling you here, I think you did quite well. I skipped chapter number 3 about raster images very early, but this is more related to raster displays, the part that are important for graphics programming, like that a pixel is the center of a cell, so you have to add or subtract 0.5. That's some things that we heard. Chapter 9 is about signal processing. I think I said that before. That is interesting, but it's not really that like you can do graphics programming without the knowledge that is in there. But of course, if you're interested, you're welcome to read it. But it's not part of the course. And chapter 12 is about data structures. I skipped most of the part there. The only part that I talked about was today about this Octrees. But we also did some other things. We talked about radiosity, shadows, and also some clipping algorithms that are not in the book. And I think you learned also a lot if you did the practicals about graphics programming, which is in the book covered in chapter 18 about graphics hardware. But actually, I think, yeah, this is a more general high level in the book and partly maybe even outdated. So I think you learned much more about graphics programming than when you did the practicals than by reading this chapter. Good. So yeah, and the following chapters of the books, for those of you who are interested in learning more about graphics, are then covering the more advanced rendering and the more advanced graphics techniques. But of course, you can also take other courses related to graphics. So I just put down a couple of courses here. So these at the top here are that are related to graphics. So these are the bachelor courses. These are the master courses. And the first three courses are the ones where it actually says that graphics is, the knowledge from graphics is required for these courses. I think the first one is not really that much related to graphics. I think this is more listed graphics as a requirement because this course, I think, has a lot of mathematics. So if you liked the mathematics of the course but not that much the actual graphics, then this might be a good course for you. Bildverwerking is of course something that is quite related to graphics, although it is similar to computer vision, which are listed here and explicitly noted that it's related to graphics because you're not doing computer graphics in vision, but you do processing of existing images, whereas in graphics you do creation of realistic images. So it's basically just complementary. But nevertheless, if you liked computer graphics, you probably also like computer vision and Bildverwerking. The two courses that are really complement this course directly are the 3D modeling and the computer animation course, which is now a lecture. It used to be a seminar, but starting next year it will be, or starting next academic year, it will be a full lecture. And this is, like I said at the beginning, the three major interests that we have in computer graphics is the 3D modeling, the rendering, and the animation. And we covered a lot about rendering in this course, and these are the other courses that complement it. Unfortunately, there is no advanced class on rendering. So there is no advanced computer graphics course here at the university, but if you're interested in computer graphics, you can always do experimentation projects or master thesis. So there are a lot of people who are not directly doing research in graphics, but doing research that is kind of related to computer graphics. Good. Yeah, but of course, before you do that, you should pass the course successfully. So the lectures are done, but not the course. There are still tutorials today on Thursday. This is also a good opportunity. So there is a last tutorial exercise sheet that I put online yesterday, and I would put the results of that online earlier, of course, so you have it in time before the exam, so at least a few days before that. And the tutorial 1 to 5 are already the results online. So you can use them for exam preparation, but you can also use the tutorials to go there and talk to the teachers and ask them about stuff from the older tutorials or other stuff that you want to know or need to know before the exam. So take that opportunity. Then, of course, we have the practicals. Deadline is Thursday at 5 o'clock, so it's already at 5 o'clock. So this time there will be no extension because we're kind of under pressure now with the grading, and you saw it, the second assignment, how long the grading can take. And because the holidays start afterwards, we have to be faster with P3, so we cannot delay it. So this is the final deadline. If you have problems with the submit system, just put it on a USB stick and give it to one of the teaching assistants who is in the room there before 5, and then they can bring it to me afterwards, and I can put it still in the system afterwards. But the system officially closes at 5. And yeah, and I have to leave at 5:30, so there is no way I can extend it. And as I said, we have additional teaching assistants present in the room. So starting today till the deadline, each day from 11 to 5, there will be at least one teaching assistant in the room. So you should have enough opportunities to get in contact with them and ask questions if you have them. But be aware that there are only 16 or 15 computers in the room, so the space is very limited. So don't do it at the very last day. It will be very crowded there, I would assume. If you usually work at home with your laptop and have a question out to the teaching assistant, it's probably a good idea to bring your laptop and then go there with your laptop and ask them, or ask them to come to another room to discuss it with you, because, yeah, like I said, experience shows that it is very crowded. So this is this unfortunate situation that we have this year, that we just have this one room. On the other hand, I think the ICT department was very helpful in setting it up, and yeah, we needed this special hardware and the special computers there. So and it worked out quite well, I think. But of course, towards the deadline, it always gets a little crowded. So be aware and plan with that. Don't come later complaining and say, yeah, I had a question, but the teaching assistant was too busy or there were no computers available. You know this now, and then you have to plan accordingly. Good. So, and then of course, after the practical, there is also the final exam next week, again, starting very early. I have to be here even an hour earlier to set everything up, so don't complain to me. It covers the lectures, everything that was not covered in the midterm exam, and also considering the tutorials. Of course, the stuff from the previous exam is also relevant here, but I will not ask an explicit question about it, but you saw how often we referred to parametric equations, normal vectors, and all that stuff. So of course you have to know that, but there will be explicit questions about the second part of the lecture, so lectures of the course, so lectures 6 till 12, and tutorials 4 to 6. Same conditions as before. I didn't bother putting it down, you know, all this, no additional material, books, calculators, and so on. Bring a pen or the pencil, all the usual student ID and all the usual stuff. Again, the exam is scheduled for 3 hours, so we start a little bit after 8:30, and then you have 2 hours. I thought about if we have 3 hours scheduled and just 2 hours starting a little bit later, but the point is 50 minutes later, earlier or later, doesn't help you very much, and it gets too much chaotic. And if we start in time, then I also have the opportunity to give you a little extra time if you still need it at the end, so I can be a little more generous and flexible. So this is why we start at 8:30, but of course the actual exam is just 2 hours. But with 200 people, we need a little extra time, also to distribute it at the end, at the beginning, and collect it at the end. In the unfortunate case that you don't make it, the retakes are scheduled August 18th, so at the end of the summer, this time at a much nicer time frame. Just a note, I will put the information about the retakes is online. I will also update it if there is a need for it on the website. So in any case, always check the website also for the exam for last minute information. Just a quick note, because I do this a little different than most of my colleagues. I have 2 separate retakes for the midterm and the final exam, because I think that's nicer to you. I think if you just screw up one of them, why should you redo both of them? So if you have had a bad first exam, make sure the second one gets better, then you just have to do one retake and not both of them. Good. Are there any questions about everything related to this course, or anything? No? No questions? Good. Then we're pretty much done. So what I usually say at the end of this course is that I hope to see as many of you as possible here, as few of you as possible here, and none of you next year, because that would mean you all passed the course. All right? Then we're done.